You think you know sand, beaches, deserts, endless dunes stretching to the horizon. It feels like the most abundant, worthless substance on Earth. But what if I told you that a specific type of sand is one of the most strategically important contested resources of the 21st century? That the entire digital world, the phone in your hand, the internet you're using, depends on a fragile, non renewable supply of this seemingly common material. We're about to explore the hidden story of how the world's cheapest sand became more valuable than gold, and why the illusion of its abundance is our greatest vulnerability. The paradox starts with a simple misunderstanding. When we picture sand, we imagine vast beaches or deserts, but that's precisely the sand we can't use. Desert sand is worthless for modern industry. Wind erosion has rounded the grains over millennia, making them too smooth to lock together for concrete. Beach sand is contaminated with salt and organic material, corroding metal reinforcements in construction. The sand we desperately need is high purity silica sand. Its value lies in two specific properties. First, angularity. It needs to be jagged, crushed from quartz rock, so the grains interlock to form strong concrete. Second, and far more critically, purity. We're talking about silicon dioxide content of 95% or higher. This isn't about building foundations, this is about building the foundation of our digital age. Extracting this specific resource is an environmental and economic nightmare. We're not just scooping it up from a beach, it requires massive open pit mines or dredging riverbeds and ocean floors. The environmental cost is staggering. River dredging destroys aquatic ecosystems, erodes riverbanks, and depletes groundwater. Coastal mining wipes out protective barriers, making shorelines more vulnerable to storms and erosion. We're literally tearing apart the planet's geographical fabric to get at this one specific type of grain, and the demand is insane. After water, sand is the most extracted solid material on Earth. We use nearly 50 billion tons annually. The vast majority, about 70 to 80%, goes to concrete for the explosive urbanization happening globally. Cities are literally built on sand. But it's the tiny high purity fraction, the stuff that makes up less than 5% of all sand used, that powers everything else. This scarcity sets the stage for a crisis we never saw coming, because we were blinded by the sheer quantity of the wrong kind of sand. So, how does this mundane material transform into the brain of a computer? The story begins in the post-WWI era with research into semiconductors. Scientists needed a material that could be precisely controlled to act as both a conductor and an insulator. That material was silicon, the second most abundant element in the Earth's crust, but almost always bonded with oxygen as silicon dioxide sand. This research cluster in California became so synonymous with the material they named the place after it, Silicon Valley. The name itself is a monument to this transformation. The process is a form of modern alchemy. It starts with raw silica sand being heated in a furnace with carbon, which strips away the oxygen, leaving behind metallurgical grade silicon. But this is still far too impure for electronics. It's about 99% pure, but in the world of chips, that 1% impurity is a deal breaker. So it undergoes a further refinement into a gas, silicon tetrachloride, which is then distilled and deposited onto a pure silicon rod, creating hyper-pure electronic-grade silicon. This polycrystalline silicon is what we need. Next comes the magic of crystal growth. This ultra-pure silicon is melted in a crucible at over 1400 degrees Celsius. A tiny, perfect silicon crystal seed is dipped into the melt and slowly pulled out, rotating as it goes. The silicon atoms from the melt aligns itself with the perfect atomic structure of the seed, growing into a single, flawless crystal cylinder called an ingot. This is the foundation. Without this perfect crystalline structure, electrons couldn't flow in a controlled way. These ingots are then sliced into wafers, those iconic mirror-finished discs that become the canvas for microchips. But a pure silicon wafer is an insulator. This is where the concept of doping comes in. It sounds negative, but it's the most crucial step. We intentionally introduce specific impurities atoms like phosphorus or boron into the crystal lattice. Phosphorus has an extra electron, creating a negatively charged semiconductor. Boron has one fewer electron, creating a positively charged semiconductor. By carefully placing these doped regions next to each other, we create transistors, microscopic switches that can be turned on and off to represent the ones and zeros of binary code. The result is a microprocessor, which is essentially a city of sand. Billions of these transistors are etched onto a sliver of silicon that started as a grain of sand. Every calculation, every app, every digital command traces back to the controlled flow of electrons through this precisely engineered landscape. It's a staggering transformation from a humble pile of sand to the most complex object humans know how to manufacture. But the story doesn't end with the chips in our devices. The same high purity silica is the lifeblood of our global connectivity. Think about the internet, the data streaming to you right now. For most of it, that journey happens through fiber optic cables, which are essentially strands of ultra pure glass. That glass is made from the same silicon dioxide, melted and drawn into hair thin fibers that act as light pipes. The principle is total internal reflection. Light enters one end of the glass fiber, and, because the silica is so perfectly pure, it bounces along the inside of the cable with minimal signal loss, carrying vast amounts of data over incredible distances. Any impurity, any stray atom would scatter the light, degrading the signal. The entire infrastructure of the internet, the cloud, and global communications relies on the optical clarity of this processed sand. Then there's solar power. The photovoltaic cells and solar panels are also made from silicon. While often a lower grade than microprocessor silicon, the principle is similar. Doped silicon creates an electric field that knocks electrons loose when struck by photons from sunlight, generating a flow of electricity. The push for renewable energy is creating another massive growing demand vector for this specific resource. This convergence of demand from construction, tech, and green energy creates a critical geopolitical pinch point. The supply chain for high purity silica sand isn't evenly distributed. It's controlled by a handful of countries with the right geological formations and the industrial capacity for purification. The United States is a major producer, but so is China, which has strategically positioned itself to control key parts of the semiconductor supply chain. This isn't just about who has the sand, it's about who has the technology to transform it. And we have to revisit the environmental cost. While we focus on the high purity sand for tech, the insane demand for construction sand is what's causing the most visible damage. Entire islands in Southeast Asia have been dredged into oblivion to feed building booms from Singapore to Dubai. River ecosystems are collapsing. This mining for one type of sand is destabilizing the environments that exist alongside the deposits of the sand we need for everything else. The two crises are inextricably linked. This scarcity doesn't just drive up prices, it fuels conflict. Around the world, sand mafias have emerged, violent criminal organizations that control illegal sand mining operations. In India, sand mining is now more lucrative than some drug trades, and hundreds of people, including journalists and activists, have been killed trying to expose these operations. It's a symptom of a resource that is both essential and becoming scarce. The tensions are international, too. The South China Sea disputes aren't just about shipping lanes, they're about seabed resources. There have been documented cases of large-scale dredging of sand for land reclamation projects, which simultaneously builds strategic artificial islands and depletes a resource needed by neighboring countries for their own development. We're seeing a new form of resource nationalism where control over sand is a tool of geopolitical leverage. This creates a profound vulnerability for our global tech supply chains. The entire digital economy rests on a foundation that is physically heavy, difficult to transport, and concentrated in potentially unstable regions. A disruption in the supply of high-purity sand from trade disputes, environmental regulations, or conflict would ripple through every industry, stalling everything from car manufacturing to smartphone production. We built a weightless digital world on a very heavy, very fragile physical base. The ultimate irony is happening in plain sight. Countries are using vast quantities of sand dredged from sensitive ecosystems to build artificial islands and coastal megacities, the very infrastructure of a connected world. But in doing so, they're potentially destroying the sources of the high-purity sand needed to power the digital connectivity those places rely on. We're consuming the foundation to build the house, creating a feedback loop of scarcity. And that brings us to the core paradox. Our perception of abundance creates a blindness to fragility. Because sand seems everywhere, we assumed it was infinite. But true value isn't about quantity, it's about specific functional properties. The right grain in the right place with the right structure is what built our civilization. The modern world isn't built on abstract data or ethereal clouds. It's built on a fragile, non-renewable resource we've taken for granted. The story of sand is a lesson in looking deeper, past the obvious abundance, to see the hidden systems and specific requirements that make our world function. It's a pattern that repeats itself with water, with rare earth minerals, With energy, the greatest risk is assuming something is cheap because it looks common. The key takeaway is that the structures we depend on are often more delicate than they appear, built on resources whose importance we only recognize once they're gone. If you want to keep exploring the hidden patterns and unexpected vulnerabilities that shape our world, make sure to subscribe.